Thank you. Okay. So, I'm going to talk to you about machine telepathy. I'm Naccache, and this week I'm going to work with those authors that I don't have the time to read. Here's what I'm going to talk about. Start by taking a PC, a standard PC. You remove from the PC all the peripherals. You enclose this PC in a perfect Faraday cage. This means that no over-the-air signal can possibly come in or out of the PC. You add around this PC a total sound isolation, protected against the Tromer-Shamir acoustic attacks. And then tamper-resistant protection to make it similar to a smart card in design. Then you produce two of those. You enclose them in a rack. As you pass by, you note my talents on AutoCAD. And then you ship everything to the Israeli-Syrian border. So why did I choose the Israeli-Syrian border? Because no information actually transits between the nations. But actually, bullets, prisoners might transit, but not information. So whatever gets here or gets there cannot possibly leak back. Now, you connect each of those PCs to a different power plant, and then you boot. And here is what can happen. The Syrian PC is going to pick a big random number, that's a 1024-bit number, and then send it to the Israeli PC, and surprisingly, the Israeli PC can echo this same number. Is this science fiction? Actually, no. We did a similar experiment between two processes running on the same PC. Each process ignored everything, even the existence of the other process. It couldn't gain knowledge of its existence through the operating system, and between two IP cores within the same FPGA. And we think, we're actually working on it now, that a random number can leap from one PC to another PC. How? Actually, PCs have an internal fan, and the speed of the fan is regulated automatically as the temperature of the motherboard. Now, an increase in processor activity will cause an increase in temperature, which in turn will cause an increase in the fan speed, which is software readable. Why you can monitor software? Because modern-day microprocessor expend a lot of heat. Here you see a cooler that goes on the top of a Pentium. Now, how do we send information? Actually, the Syrian sets a point, and then he uses a classical signal regulation algorithm, which is called PID. Proportional integral derivative regulation, that allows it to control the fan speed here. E is actually measuring the fan speed over time, and you can set a target and then have this target achieved. Now, once the fan is turning at this target, the Israel is going to read the speed and then transmit 1 bit per 3 minutes. We implemented it successfully on two different platforms, on a PC and on a Mac. Two different platforms. Here you see the Syrian communication log saying hello to the Israeli, and here is how we modulate it. And here is the communication log of the Israeli reading the same information. Now, what you can see here is the angular speed in radians per second of the fan over time. This is not the temperature, but it is highly temperature correlated. It is nearly the temperature. And you can see here several levels. I actually modulate using the amplitude, the information that I want to transmit. So I have level 0, level 1, level 2, and level 3. Now if I remove the graphic and I leave just this sequence of numbers, I invert their order, I split them into bytes, I translate it into hexadecimal, I reverse the order again, and I translate it into ASCII. Now, we have this device, which is actually a rack containing 8 PCs. This is something like 50 kilos. And we want to transmit between card 8 and card 7 information. So one card is going to hit the temperature, to raise the temperature inside the device, and then the other card is going to read it. There are other variants. You can use processor load using a Java virtual machine to establish covert communication outside of the virtual machine. There is even a flag inside the Pentium telling you that there is an overheat that you can go and read, and this way you can transmit information. You can also try to listen to the speed fan using the PC's microphone. Discs have something which is called SMART, which is actually an IBM standard to allow you to read all sorts of parameters. One of those parameters is temperature, so you can do exactly the same thing on a hard disk. We actually implemented it. And you can also try to provoke Rump faults, and whenever the readback of the Rump doesn't work, this only works on very low quality machines, then you can transmit information inside the machine. Now, the naval postgraduate school developed for the NSA for Chinese design, which is called the moat and draw bridge. This design was meant to avoid cover communications between different IP cores inside the same FPGA. How do they use it? They use some CLBs in the FPGA as dedicated transmission means, and they use a special synthesis tool. So this is, for instance, a core where you can see 3 cores. This one done, let's say, by the NSA, and these 2 by 2 developers. And they coexist on the same FPGA. The problem is that, as you can see, there is the area where there is an intersection. So the synthesis tool is actually going to reserve some CLBs for the purpose of communication between these processes. So when this process disconnects those CLBs, there is no way for the others to communicate with it. What we've done is the following: implemented using pure digital design, a heat source and a heat sensor. How do you design a heat sensor and a heat source using pure digital means to transmit information? We achieve 1 bit per second, and here is how it's done. To generate heat, it's very easy. What you do is simply a ring oscillator. What is a ring oscillator? It's an odd number of inverters. So information is actually chasing itself over and over and over again. You put several of those. You can enable the heat generation or stop the heat generation, and then when you want to heat the chip, to raise the temperature, you just enable it and you start expending energy. How do you sense heat using digital means? Well, also using a ring oscillator, because the frequency at which the ring oscillator is oscillating is very much dependent on the temperature. So variation in temperature can be sensed by pure digital means. How do you do it? You have a very big shift register in which you have simply a sequence of ones which is transiting, and you're going to use the reading of the position of the one in order to determine where it is. Several countermeasures, guard process, and the most interesting is probably relocate data centers to Alaska. And finally, for the secret agents in the ocean, I know there are several. So, Naccache even industry is now marketing the thermal bag. So what is the thermal bag? This is the thermal bag that you can see here. I designed it, so you have a big microcontroller. Here you have a serial histogram into which you can store data. You have a switch to trigger it on, infrared interface, 2 LEDs that allow you to control it and do dialogue with it. And then on the back side, the solid state temperature sensor, the battery, and using this artifact, you can actually glue it behind the PC and then record information. So here you see the PC, and here I'm gluing it, then we remove it, then using this device, which is the infrared reader, you can read the information back. So this is what I had to say. I have 50 CDs here with source code, schematics, if you want to play with it. Everything is here. First come, first serve. Thank you.